Newton's law of viscosity in the chemical industry. Fluid dynamics is the study of a fluid in motion. Assessing the fluid dynamics has a vast importance in the chemical industry. Chemical engineers can use knowledge of fluid dynamics to understand things like fluid transfer and quality control. This will help an engineer to understand the working structure of a fluid and manipulate the fluid successfully as per needs of specific industry applications. Newton's law of viscosity states that the shear stress of a fluid is directly proportional to the rate of shear strain. Viscosity of a fluid is the property of a fluid to resist the rate at which deformation takes place when the fluid is acted upon by shear forces. Understanding viscosity is an important factor in design and operation in chemical industry. In the chemical industry and manufacturing processes, viscosity measurements are used to optimize the productivity and efficiency of a process. Viscosity measurements are also monitored during production to ensure that each batch is consistent and produces the desired viscosity and texture of a product.
All fluids are either Newtonian or non-Newtonian. A fluid is Newtonian when viscosity remains constant, regardless of the amount of shear applied at a constant temperature. Newtonian fluids have a linear relationship between viscosity and shear stress. Common examples of Newtonian fluids are water, gasoline, and alcohol.
In this demonstration with the Newtonian fluids such as water, stress is applied by the golf ball. And whether stress is applied by just placing the ball in the water, or when greater stress is applied by dropping the ball from a height, the viscosity of the Newtonian fluid appears the same.
As mentioned before, Newtonian fluids have a linear relationship between viscosity and shear stress, which is shown on this graph. As for non-Newtonian fluids, shear thickening and shear thinning, the viscosity changes when shear is applied. We will consider both the shear thickening and shear thinning fluid. The viscosity of the fluid increases when shear is applied and is known as shear thickening. This behavior is shown in quicksand, cornstarch and water mixture, and silly putty.
In our demonstration, we are mixing cornstarch and water together. When the golf ball is placed in the mixture acts as a fluid and the ball sinks to the bottom. But when a greater amount of stress is applied and the ball is dropped from a height, the viscosity of the fluid increases. The mixture behaves as a non-Newtonian shear thickening fluid. During high pressure and high velocity processes, shear thickening fluids behave like solids and have a greater viscosity. This is because the molecules crowd around each other and resist flow.
The next example of a non-Newtonian fluid we consider is shear thinning fluid. A shear thinning fluid experiences a decrease in viscosity when shear is applied. This is observed in the everyday condiment ketchup.
You can see that when the ball is placed in the ketchup, it slightly sinks towards the bottom. But as more shear stress is applied, the ketchup experiences shear thinning behavior. There is a decrease in viscosity and the ketchup splatters everywhere. We can also consider ketchup as a shear-sensitive fluid. Since all fluids do not react the same way under pressure, their response to shear forces is described as shear sensitivity. Another demonstration can be seen when a small amount of pressure is applied to the ketchup bottle. It comes out slowly and appears thick. If more pressure is applied to the bottle, it releases more easily and the viscosity decreases, demonstrating a shear thinning behavior.
Shear acts in the direction parallel to pump and tube surfaces. Viscosity and interior pipe surface smoothness is related to the resistance of shear in fluids. When considering fluid motion in a pipe, which is common in the chemical industry, the velocity profile is parabolic. At the wall of the pipe, the fluid experiences the greatest amount of shear stress, and the velocity is equal to 0. Alternatively, at the center of the pipe, the fluid experiences little to no shear stress and the velocity profile is at its maximum. Non-Newtonian fluids moving through a pipe are subject to shear forces, which can cause a change in viscosity. The change in viscosity results in shear thickening or shear thinning fluids. Newtonian fluids do not have to worry about shear forces affecting the fluid viscosity.
I'll be talking about the applications of viscosity during my co-op experience at Johnson & Johnson on Lidditz, PA. At this site, quality control is a crucial part of the consumer goods industry since manufactured products must adhere to strict levels of consistency. So for products like Listerine, Neosporin, and Lubriderm, and other products manufactured by J&J, this is very necessary. Viscosity is one measure that quality control utilizes to test the readiness of a particular product. So how to measure viscosity? In principle, viscosity can be measured by the time it takes for a volume of fluid to flow under gravity through a capillary viscometer. And on the image on the slide, you can see what a viscometer looks like. However, at the J&J plant site in Lidditz, where a large amount of product is moving out daily, it's necessary to achieve a higher level of accuracy and precision. So in order to find more accurate measures of viscosity, rotational viscometry was developed. So finding viscosity using rotational viscometry. Product is run through a cup containing a spindle, and the amount this spindle rotates generates a value for torque. Looking at the equation below, coefficients can be used to determine a value for apparent viscosity. These coefficients depend on things like the approximate viscosity range of a substance and the type of spindle being used. For viscosity ranges, these can be low, medium, or high. A low range may include a substance or a product like Listerine, which is a mouthwash. For medium viscosity, it may be a lotion like Lubriderm. And for high viscosity, it could be an ointment like Neosporin. So interpreting viscometry data. So it's important to find the viscosity of a finished product. However, this doesn't tell the whole story. Engineers want to know if a substance will exhibit shear thickening or shear thinning behavior when used by consumers. So it's important to forecast the viscosity of substances during production and during application by consumers. This can be done by calculating yield point values from flow curves, which are derived from mathematical regression models. On the image, you can see a couple of examples, such as the Herschel-Bulkley fluid model, which is one that is used to determine values such as the product's yield stress, flow index, and consistency index. Comparing data to these models allows engineers to formulate substances accordingly. So applications to Neosporin. Neosporin is one product which is formulated, manufactured, packaged, and shipped from the Johnson & Johnson Lidditz site. This product is an ointment, which means it must show shear thinning behavior when squeezed from a tube and applied to the body. So once engineers have picked a formulation, a consistency must be chosen that matches the appropriate stability and flow characteristics. Since the Lidditz site is one of the primary Neosporin manufacturers based in the US for J&J, this is critical that quality control and validation get this value right. And so part of my job at J&J was helping the validation department collect data samples over a long period of time and compiling any changes in viscosity and fluid characteristics. This allowed us to make adjustments when necessary based on external factors that might be unforeseen, such as new ingredient suppliers or new manufacturing equipment.
Switching gears, but still talking about industry, at BASF Monaca, my co-op site, there's two different types of latex products being produced, one called acrylonol, one called butanol. Acrylonol is made by acrylates, where butanol is made by a styrene and butadiene type of latex. Anyone who's dealt with raw latex knows it's a very sticky material, which means it's very viscous. So there's two different perspectives that I really wanted to take here. And the first one is our on-site perspective. The first thing that we experience at the Monaca site is the clogging of pipes, and this is largely due to Newton's law of viscosity. As Nikki mentioned, the velocity at the edge of the pipe is 0, where the shear force is the greatest. So over time in a real fluid, the latex ends up building up and up and up, which could cause skins in the pipes, which could cause the pumps that pump out the product to deadhead. High pressure water blasting is usually used intermittently to clean the pipes, but sometimes it's not tracked very well and the pumps deadhead, causing some sort of overpressure. So here is what deadhead really means. Engineers use pump curves to define deadhead, which is a relationship between the head pressure, which is the pressure discharge of the pump, versus the flow. So essentially, the pump is overpressuring and there's nowhere for the fluid to go. Eventually, this causes a lot of PHA issues, process hazard analysis, meaning that we could overpressure a pipe or a pump, causing shrapnel to blow either the pipe or the pump apart because they're not rated for the high pressures by the pump. In terms of the customer application, the latex is shipped to various different customers and used in like bare paint, many paper products, as well as coatings for the outside of people's houses. And each of the different acrylonol and butanol products have different viscosities. So if it's not in spec, the product is not going to perform to what it's supposed to. So each different product essentially is different. This has a different viscosity, having it have different applications in different situations. So for example, a paint, you may want a latex that is not very viscous, whereas a coating on the outside of someone's house, you may want it to be very viscous. And that is it.